All right, let's explore. Number 12, the bootstrap paradox. In 1941, science fiction writer Robert Heinlein published a story called By His Bootstraps, in which a man travels back in time and becomes trapped in a causal loop with no beginning and no end. Physicists spent decades dismissing it as fantasy. Then they looked more carefully at their own equations, and the fantasy started looking uncomfortably familiar. The expectation in classical physics was straightforward. Cause precedes effect. Every event has an origin. The universe keeps its ledger in order, and information, like matter, has to come from somewhere. These were not controversial assumptions. They were the invisible architecture beneath every scientific theory ever written. Then came the problem. Einstein's field equations of general relativity, published in 1915, permit a class of solutions called closed time-like curves, paths through spacetime that loop back on themselves. In 1949, mathematician Kurt Gödel demonstrated this directly, presenting a rotating universe model to Einstein himself at Princeton, in which time travel was not just possible, but mathematically required. And closed time-like curves contain a feature that has no solution. An object or piece of information can exist in a loop with no point of creation. Consider what that means. A time traveler carries a book back to the past, gives it to an author who publishes it, and the traveler later reads that published book and carries it back. The book was never written. It simply loops, forever, without origin. Physicist Igor Novikov formalized this in his self-consistency principle in the 1980s, and Stephen Hawking proposed his chronology protection conjecture in 1992 to rule it out entirely. That conjecture has never been proven. Causality, the principle that every effect has a cause, is the foundation of all scientific reasoning. The bootstrap paradox does not bend that foundation. It removes it. And the equations that describe our universe insist it is allowed. Number 11, the arrow of time paradox. Write down any fundamental equation in physics. Newton's laws of motion, Maxwell's equations of electromagnetism, Schrödinger's equation in quantum mechanics, Einstein's field equations. Now run time backwards. Every single one of those equations works just as well in reverse. The physics does not care which direction time flows. So why do we experience only one? This is not a casual observation. It is a profound structural feature of physical law that has puzzled physicists for over a century. Our experience of time, the irreversible movement from past to future, from cause to effect, from birth to death, is the most fundamental fact of human existence. It is also completely absent from the equations that are supposed to describe existence. The one apparent exception is the second law of thermodynamics, which states that entropy, the measure of disorder in a system, always increases over time. A shattered glass does not reassemble. Smoke does not return to a match. Ludwig Boltzmann formalized this connection between entropy and time in the 1870s, and it remains our best physical explanation for why time has a direction. But the second law is statistical, not fundamental. It describes a tendency, not a rule. In principle, a shattered glass could reassemble. It is simply extraordinarily improbable. Physicist Sean Carroll of Caltech has argued extensively that the arrow of time requires a cosmological explanation, not a thermodynamic one, proposing in his 2010 book, From Eternity to Here, that the direction of time is inherited from the universe's extraordinarily low entropy initial state at the Big Bang, a condition that itself remains unexplained. Philosopher of physics. David Albert at Columbia University calls this the past hypothesis and notes that we have no theory that predicts it. We experience time's direction as the most obvious fact of existence. Physics tells us it should not exist. One of them is wrong, and we do not know which. Number 10. The quantum measurement problem. On October 24th, 1927, the greatest gathering of physicists in history assembled in Brussels for the Fifth Solvay Conference. Albert Einstein, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Wolfgang Pauli, and 20 other architects of modern science sat in the same room to confront a question that their own theory had raised and could not answer. Nearly a century later, that question remains open. Quantum mechanics describes particles through a mathematical object called the wave function, which represents all possible states a particle can occupy simultaneously, a superposition of every position, every momentum, every property at once. This is not an approximation. Experiments confirm it with extraordinary precision. Quantum electrodynamics, the theory built on this foundation, is the most precisely tested theory in the history of science, with predictions matching experiment to 12 significant figures. But something happens when you measure a quantum particle. The superposition vanishes. The particle, which existed in all possible states, snaps into one definite state. This is called wave function collapse, and here is the problem. There is no equation in quantum mechanics that describes it. The theory tells you everything about what happens before measurement, and everything about the probabilities of outcomes. It says nothing about the transition between them. In 1935, Erwin Schrödinger designed his famous cat thought experiment specifically to expose how absurd this is. A cat in a box, linked to a quantum event, would be simultaneously alive and dead until observed. Schrödinger intended this as a reductio ad absurdum. He expected the theory to be fixed. In 1957, Princeton doctoral student Hugh Everett III proposed the most radical resolution. The wave function never collapses. Every possible outcome actually occurs in branching, equally real versions of the universe. His supervisor, John Wheeler, spent months urging him to soften the claim. Everett refused. If the act of observation determines physical reality, what was the universe doing before anything existed to observe it? Number 9. The grandfather paradox, and why physics might actually allow it. In September 2020, physicists Germain Tobar and Fabio Costa at the University of Queensland published a peer-reviewed paper in the journal Classical and Quantum Gravity, with a finding that should have made headlines far beyond academic physics. They were not writing science fiction. They were solving differential equations. And their solution suggested the grandfather paradox does not make time travel impossible. It makes free will impossible. The grandfather paradox is the classic objection to time travel. If you travel back and kill your grandfather before your father is born, you cannot exist to make the trip. The contradiction seems to rule out time travel entirely. For most of the 20th century, that was the comfortable consensus. Closed time-like curves, the technical term for time travel paths permitted by Einstein's general relativity, were treated as mathematical curiosities rather than physical possibilities. Tobar and Costa's calculation showed something deeply unsettling. In a spacetime that contains closed time-like curves, self-contradictory events do not produce paradoxes. Instead, the mathematics forces consistency automatically. Events adjust. If you travel back to kill your grandfather, something will prevent you. Not a physical barrier, not a law you can identify, but a systemic constraint built into the geometry of space-time itself. The universe does not stop you from making the trip. It stops you from completing the action. Stephen Hawking's 1992 chronology protection conjecture, published in Physical Review D, was the most influential attempt to simply prohibit time travel at the level of physics. It has never been proven. Meanwhile, Kurt Gödel demonstrated in 1949 that closed time-like curves are valid solutions to Einstein's field equations, and they remain so today. Physics does not rule out the grandfather paradox. It rules out your ability to cause it, which raises a question about every choice you believe you are making right now. Number 8. The fine-tuning problem. There are somewhere between 19 and 26 fundamental physical constants that govern the behavior of the universe. The speed of light, the gravitational constant, the mass of the electron, the strength of the strong nuclear force. None of these values are predicted by any theory. They are simply measured, written down, and accepted. And when physicists examine what happens if those values are even slightly different, the results are catastrophic. The universe is not just compatible with life. It is calibrated for it with a precision that has no scientific explanation. Change the strength of the strong nuclear force by 2% in either direction, and either hydrogen never forms or protons become unstable. Both outcomes end the universe before it begins. The cosmological constant, the value associated with dark energy, is fine-tuned to approximately 1 part in 10 to the power of 120. Physicist Paul Davies explored these relationships in his 1982 book, The Accidental Universe, and Martin Rees cataloged 6 critical constants in his 1999 book, Just 6 Numbers, noting that even tiny deviations in any of them would produce a lifeless cosmos. The most striking individual case belongs to astronomer Fred Hoyle. In 1953, Hoyle predicted that carbon-12 must possess a specific nuclear resonance level at approximately 7.65 million electron volts. Not because theory demanded it, but because carbon-based life exists, and without that resonance, stars could not produce carbon. The resonance was found exactly where he predicted, confirmed by William Fowler's team at Caltech. Hoyle later wrote that the universe looked like a deliberate arrangement. He was not a religious man. He simply could not find another word for what the numbers implied. 3 explanations exist: pure chance, the anthropic principle, or the multiverse. None is scientifically testable in the traditional sense. The universe appears designed. We cannot explain why. Number 7. The black hole information paradox. In 1974, Stephen Hawking published a paper in the journal Nature titled, with characteristic understatement, Black Hole Explosions. The paper demonstrated mathematically that black holes are not entirely black. Due to quantum effects near the event horizon, they slowly emit thermal radiation and, over vast timescales, evaporate completely. The discovery was celebrated as a triumph. Then physicists realized what it implied. Hawking had not solved a problem. He had created the most profound one in modern physics. The radiation Hawking described is thermal. It is random, featureless, carrying no information about what fell into the black hole. A star, a library, a human being, they all contribute identically to the glow. When the black hole evaporates completely, that information is gone. In quantum mechanics, this is not permitted. The principle of unitarity, one of the theory's foundational requirements, states that information is never destroyed. The total information content of the universe must be conserved. General relativity says information can be destroyed. Quantum mechanics says it cannot. Both theories are foundational. Both are extraordinarily well tested. They cannot both be right. The conflict became known informally as the Black Hole War. Hawking argued for decades that information was genuinely lost, accepting the revision to quantum mechanics. Physicists Leonard Susskind and Gerard T. Hooft argued the opposite, developing the holographic principle in the early 1990s, which suggests all information about a black hole's contents is encoded on its two-dimensional event horizon surface. At a conference in Dublin in July 2004, Hawking publicly conceded. He accepted that information is somehow preserved. He did not know how. In 2019, calculations using a framework called quantum extremal surfaces suggested a mechanism for information escape, but the mathematics remains deeply contested. We do not know whether the universe keeps records of itself. Number 6. Quantum entanglement and non-locality. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper in Physical Review that they believed exposed a fatal flaw in quantum mechanics. The theory implied, they argued, that measuring one particle could instantaneously affect another particle arbitrarily far away. Einstein called it spooky action at a distance and considered it proof that quantum mechanics was incomplete. He spent the rest of his life convinced the theory needed to be replaced. He was wrong about the conclusion, but exactly right about the phenomenon. Quantum mechanics predicts that two particles can be entangled, placed in a shared quantum state, such that measuring one instantly determines the state of the other, regardless of the distance between them. For decades, physicists hoped this could be explained by hidden variables, some additional information carried by the particles that quantum mechanics simply did not account for. In 1964, physicist John Bell devised a mathematical theorem that made this testable. He calculated a specific statistical threshold that any hidden variable theory would have to satisfy, published in the journal Physics. Alain Aspect and his team at Université Paris-Sud ran the definitive experiments in 1982. The results violated Bell's threshold. Hidden variables could not explain the correlations. The entanglement was real, and it was non-local. In 2017, a Chinese satellite called Meteus demonstrated entanglement maintained over 1,200 kilometers. In October 2022, Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics specifically for this experimental work. The physics community's formal acknowledgement that something deeply strange about space has been confirmed. No information travels between entangled particles faster than light. The no communication theorem ensures that. But the correlation happens faster than any signal could account for, as if the space between them is not a meaningful barrier. If space does not separate entangled particles in any physically meaningful way, what is space for? Number 5. The simulation paradox. In 2003, philosopher Nick Bostrom at the University of Oxford published a paper in the Philosophical Quarterly titled, "Are You Living in a Computer Simulation?" It was not a thought experiment. It was a logical proof. Bostrom demonstrated that at least one of three statements must be true, and every option is more disturbing than the last. No one has successfully refuted the argument in the 2 decades since. The trilemma runs as follows. Either virtually all civilizations capable of running detailed simulations of conscious minds go extinct before reaching that capability, or virtually all such civilizations choose never to run them, or we are almost certainly living in a simulation right now. The logic is probabilistic. If simulations are ever run in large numbers, simulated conscious minds will vastly outnumber biological ones. Assuming we are not in a specially privileged position, we are almost certainly in the majority. And the majority, in that scenario, are simulated. What makes this genuinely unsettling, rather than merely philosophical, is that physics provides potential corroboration. In 2012, physicist Silas Bean and colleagues published a paper in the European Physical Journal A, suggesting that simulated universes might have detectable signatures, specifically constraints appearing at the smallest possible scale of space. The Planck length of approximately 1.616 times 10 to the negative 35 meters. The universe's laws are mathematical, with a precision that physicist Eugene Wigner called the unreasonable effectiveness of mathematics in a landmark 1960 essay, noting that abstract mathematical structures invented for purely theoretical reasons keep turning out to describe physical reality with uncanny accuracy. No experiment you could perform would definitively prove you are not in a simulation. Every measurement you take, every result you record, every sensation you experience could be generated output. There is no test from inside the system that reaches outside the system. Reality itself may be a question that physics cannot answer from within. Number 4. The Boltzmann brain paradox. Ludwig Boltzmann, the Austrian physicist who formalized the connection between entropy and time in the 1870s, died by suicide in September 1906, in part from the professional rejection his ideas received. One of those ideas was so disturbing that the physics community initially preferred not to follow it to its conclusion. When they finally did, they found it waiting for them at the center of modern cosmology, embedded in the mathematics of the universe's future. Boltzmann recognized that thermodynamic fluctuations are statistical. In a sufficiently large and sufficiently old universe, even highly improbable configurations of matter will eventually occur. A fully formed star could assemble from random particle collisions. So could a planet. So could a brain, complete with a lifetime of memories, a sense of self, and a vivid experience of existing in a world. Boltzmann proposed that the observable universe might itself be such a fluctuation in an eternal, higher entropy cosmos. The argument was not dismissed because it was wrong. It was set aside because it was disturbing. The modern version is more precise and more troubling. Our current cosmological models, supported by extensive observational data, indicate that dark energy will drive the universe into an eternally expanding de Sitter space. In that geometry, quantum fluctuations continue indefinitely. Physicists Sean Carroll and Kim Boddy have published work arguing that de Sitter space produces self-aware structures, Boltzmann brains, at a calculable rate, and that in an eternal expansion, these structures will eventually outnumber brains that arose through billions of years of biological evolution. Standard probability then implies that you are almost certainly one of them, a fleeting fluctuation that assembled moments ago with false memories of an entire life. The paradox cannot be escaped by appealing to your memories or sensory experience. A Boltzmann brain would have both. Number 3. The Anthropic Shadow and the Great Filter. In 1998, economist and philosopher Robin Hanson at George Mason University published a paper titled "The Great Filter, Are We Almost Past It?" It began with a simple observation. The universe is approximately 13.8 billion years old, contains hundreds of billions of galaxies, each with hundreds of billions of stars, and a significant fraction of those stars host rocky planets in habitable zones. By any reasonable estimate, the conditions for life have existed countless times across cosmic history. We should be surrounded by evidence of other civilizations. We see nothing. That silence requires an explanation. Hanson's explanation was the most unsettling possible. Something filters virtually all paths to spacefaring civilization, and we do not know whether we are before it or past it. Enrico Fermi articulated the core paradox at Los Alamos in the summer of 1950, in what colleagues recalled as a lunchtime conversation that ended with the question now bearing his name: where is everybody? The cosmic silence has only deepened since. 60 years of systematic radio telescope searches have returned nothing unambiguous. Physicist Brandon Carter formalized a related argument, the doomsday argument, in 1983, applying the Copernican principle to humans. Assuming our position in the timeline of our species is not special, we are statistically more likely to be near the end of humanity's total lifespan than at its beginning. The anthropic shadow makes this worse. Any catastrophe that killed all previous observers cannot be observed by those previous observers. By definition, only survivors study history, which means our own survival tells us nothing meaningful about the risks still ahead. We are systematically blind to the existential threats most likely to eliminate us, precisely because the ones that nearly succeeded are the ones that left no one to study them. Nick Bostrom has argued that discovering microbial life on Mars would be the worst news in human history. If life arises easily, the filter is almost certainly ahead of us. Number 2, the many worlds interpretation and the reality of everything. In 1957, a 27-year-old Princeton doctoral student named Hugh Everett III submitted a thesis that proposed quantum mechanics was simply correct, without exception or modification, applied to everything, including measuring devices, laboratories, and physicists themselves. His supervisor, John Wheeler, spent months urging him to soften the language. Everett refused to change a word that mattered. What his thesis implied was that every quantum measurement causes the universe to branch, with every possible outcome occurring in a separate, equally real world. Not metaphorically, physically. Right now, as you read this, copies of you are reading the last word of a sentence that ended differently. The Many Worlds interpretation, published in Reviews of Modern Physics in July 1957, resolves the measurement problem completely. The wave function never collapses. It branches. There is no mysterious transition between quantum possibility and physical reality. All the possibilities become real. This is why physicists David Deutsch at Oxford and Max Tegmark at MIT have argued forcefully that Many Worlds is the most scientifically honest reading of quantum mechanics, and why informal polls at major physics conferences now show it is the plurality-favored interpretation among working physicists. The cost of this resolution is ontological extravagance on an incomprehensible scale. Branching occurs with every quantum interaction, across every particle, in every cubic centimeter of space, constantly, generating an effectively infinite proliferation of parallel histories. Every path you did not take exists. Every death you did not die is happening. Every version of your life that quantum mechanics permits is unfolding in a universe indistinguishable from this one, populated by people who have no idea they are one of countless iterations. Everett himself received almost no recognition during his lifetime. He died in 1982, largely ignored by the field he had transformed. The question of which branch you are in, and what it means to be you rather than any of your counterparts, is one that the mathematics of many worlds raises with perfect precision and refuses completely to answer. Number 1. The hard problem of consciousness. In 1995, philosopher David Chalmers at the Australian National University published a paper in the Journal of Consciousness Studies titled Facing Up to the Problem of Consciousness, and in it he drew a distinction that has since become one of the most contested boundaries in science. There are, he argued, the easy problems of consciousness, explaining how the brain integrates information, directs attention, reports internal states, controls behavior. These are difficult, but they are tractable. More research, more data, better models, and they will eventually yield. Then there is the hard problem. Why does any of it feel like anything? That question is not a matter of missing data. It is a matter of category. No physical description of a brain, however complete, contains the fact of experience. Neuroscientist Francis Crick and physicist Christoph Koch launched the Neural Correlates of Consciousness program in 1990, systematically identifying which patterns of brain activity correspond to conscious states. They found the correlations. They could not explain why those correlations are accompanied by experience at all, why the firing of neurons in a particular configuration produces the redness of red, the painfulness of pain, the sense that there is something it is like to be you. Philosopher Thomas Nagel established the core of this problem in his 1974 paper, What Is It Like to Be a Bat?, published in the Philosophical Review. No amount of physical description of echolocation, he argued, will tell you what it subjectively feels like to be a bat. The subjective is categorically absent from objective description. The leading scientific frameworks do not close this gap. Giulio Tononi's integrated information theory, proposed in 2004, and Bernard Barz's global workspace theory, developed in 1988, identify structural features associated with consciousness, but neither explains why those features are accompanied by experience rather than occurring in the dark. Physicist Roger Penrose, in The Emperor's New Mind, published in 1989, argued that consciousness requires physics we do not yet have. Philosopher Philip Goff, in Galileo's Error, published in 2019, has argued that consciousness may be a fundamental feature of reality itself. present at every level of nature, not generated by complex systems, but irreducibly basic, like mass or charge. Chalmers himself takes this possibility, called panpsychism, seriously, not as a mystical claim, but as a logical consequence of the failure of every physicalist account. Every paradox in this video was discovered by a conscious mind, confronting a universe it could not fully explain. The bootstrap paradox, the arrow of time, the measurement problem, the fine-tuned constants, the entangled particles, the branching worlds, all of it, found and named and puzzled over by beings capable of wonder. Physics can map the architecture of space-time, trace the quantum behavior of particles, calculate the fate of the cosmos across trillions of years. It cannot explain why any of it feels like something. It cannot explain why there is a subjective inside to the universe at all. That is not a gap that better instruments will close, or a question that more data will answer. It is the place where physics meets its own edge. And standing at that edge, looking out at everything we do not understand, is a conscious mind that has no physical account of how it got there, or why it can look at all. If you want to see more videos like this, click the video on screen now and make sure to subscribe.